Hello, my name is Sean, and today we're going to be working through Griffith's 3.35. The question asks to find the electric field at a point sufficiently far away from a charged sphere whose charge density is given by a positive rho naught in the northern hemisphere and a negative rho naught in the southern hemisphere. The sphere is a radius r. Now first we can recognize that in multipole expansion there's going to be no monopole term because the total charge is going to be 0, as we can see from the equal and opposite charge distributions, or charge densities. So the first non-zero term is going to be the dipole term. So we have our equation for the dipole potential, which is 1 over 4 pi epsilon naught, r hat dot our dipole moment over r squared, where our dipole moment of a charge distribution is going to be given by the volume integral of our sphere of our charge density, our source vector, and our volume elements. So first, to define all these terms, we're going to have two charge densities. So we're going to have a rho on top, and that's going to be equal to our positive rho naught, and our rho on bottom, which is going to be equal to our negative rho naught. Our r prime is going to be equal to, just simply in Cartesian, x hat plus y hat plus z hat, and our volume element term is going to be given by in spherical r squared sine theta d theta d phi d r, and since this is a source element, d tau prime, these should all be primed, but it won't affect our calculation if we leave that out, and for clarity's sake I'm going to do that. Another thing to note is that due to the symmetry of the situation, where we have all these positive charges on top, negative charges on bottom, every negative charge is going to have a corresponding positive charge in the z direction, and there's going to be obvious cancellations in any direction that isn't the z direction. So we're only going to be considering our z element. Now it will also be useful to note, since we're going to want this in spherical coordinates, that z is going to be equal to r cosine theta. Since theta is just measured from the z-axis, it's just going to be the projection of r onto the z-axis. Now to simplify things further, we can recognize that we're going to have the sum of these two integrals for each charge density. The only difference, though, is that this has a positive rho naught and this has a negative rho naught, except this bottom integral is going to be going from pi over 2 to pi, but we can match that to the integration bounds of our first integral, because the sine theta element won't be affected by that change, and the cosine theta element that's going to be in there will simply flip signs, which will cancel out with the sign of this negative rho naught. So we can see that in action here when we can just set up our integral finally. Set it up over here. Our dipole moment is going to be equal to the integral from r equals 0 to r, our radius, from phi equals 0 to 2 pi, and from theta equals 0 to pi over 2. Oh, and this is of course the sum of these two integrals, so of two identical integrals. So we're going to have a 2 out in front, and we're going to have our rho naught times our z hat, since we're only considering the z component, and our d tau. Now to break this up into something a little more clear, we can have our rho naught out in front, and we have our r element. Oh, and of course this z is just going to be r cosine theta. So this r, and then we get r cubed, dr. We get phi from 0 to 2 pi, and we have no phi except for our d phi. And then we have our theta from 0 to pi over 2 of our sine theta cosine theta d theta. And this is all in the z hat direction. Now we just solve our integral to rho naught. We get 1/4 r to the 4th, evaluated from 0 to r, and we get just 2 pi for our phi. And doing a quick u sub here, we could set u equal to sine theta. So du is going to equal cosine theta d theta. D theta equals 1 over cosine theta du. And our bounds are going to be sine of 0, which is 0, to sine of pi over 2, which is 1. So 0 to 1, this cosine theta is going to cancel that cosine theta, get u du, and then all that times z hat. So just simplifying further and solving that integral, we get 2 rho naught r to the 4th over 4 times r 2 pi times r 1/2 u squared evaluated from 0 to 1, the z hat direction, finally getting rho naught r to the 4th pi over 2 z hat. Now plugging that in to our dipole potential, we will get our 1 over 4 pi epsilon naught, and then just pulling out everything. Oh, and then our 1 over r squared, and then pulling out everything that isn't just our z hat, r to the 4th times pi over 2, and then we're just going to have that r hat dotted with our z hat, and this is just going to be cosine theta because its magnitude is 1. Same reasoning as over here, all just to get rho naught r to the 4th cosine theta all over 8 epsilon naught r squared. We're not done yet though, as we need to find the electric field, which is given by our negative gradient of the potential we found. And in spherical, this is going to be negative r partial with respect to r times our potential in the r hat direction, and then plus 1 over r partial with respect to theta of our potential in the theta hat direction. And we know we don't have any phi components, so I'm just going to disregard that. And just to simplify things, I'm just going to take this term and call it e sub r, this term, call it e sub theta, just solve for each one of those. So our e sub r will equal, then pulling out everything that we don't really care about with respect to the partial derivative, over 8 epsilon naught, and then what we do care about, which is that 1 over r squared, the partial derivative of which is just going to be negative 2 over r cubed, and then our e sub theta element is going to be our 1 over r times all that stuff that doesn't matter for our partial, r squared, and then that partial derivative. And that partial derivative is just going to be affecting cosine theta, which will become negative sine theta. And now when we plug these elements back into their vector form, we're going to have many like terms. So we're going to get that the electric field is equal to our like terms, which is rho naught r to the 4th over 8 epsilon naught r cubed, and then we'll just have those non-alike terms connected to their respective unit vectors, which is going to be our 2 cosine theta, 2 and our cosine theta, connected to our r hat, plus our sine theta connected to our theta hat. And this is our electric field using the dipole approximation at a point far away from the sphere. Thank you very much for watching.